Hello everyone, today we're going to be talking about special relativity, and this is of course by me, Abdin Habibi. So let's talk about special relativity. Albert Einstein, at the young age of 26, published a paper that spoke on special relativity, and 10 years later he released a improved version of this theory that is what is regarded as today as general relativity. And this changed science and physics as a whole and forever cemented his name in history.
Hello, everyone. So we just talked a bit about the history of special relativity. So let's get more into the nitty-gritty of special relativity. Before we can actually talk about that, we need to talk about some other things. So if you remember from grade 11, we talked about frames of reference. And if you are not sure what that is, I'll tell you what it is right now. So in physics, what a frame of reference is an arbitrary abstract coordinate system. For example, let's say it's you, okay? This is you. A coordinate system would be like your eyes are the origin. I'm not the best drawer. And basically, you scale it off where your eyes are. So you kind of create this. Well, in our case, since we see in 3D, you'd create a 3D coordinate system. Now, and it's set by reference points. For example, if you're looking at something, and we use these scales and frames of reference to identify things mathematically and physically. Now, in relativity's case, we have something called inertial frames of reference, which is spelled like this: inertial frames of reference. Okay? So, inertial frames of reference. Now, what inertial frames of reference are is basically frames of reference, often dealt with in physics actually. You might have dealt with it before, and it's where Newton's laws are satisfied. So let's go over some of Newton's laws. If you don't remember from the 2 units before, in the forces unit, we did talk about Newton's laws. So the first one is actually the law of inertia. And we're going to be talking about this, don't worry. This is important, yeah, I'm sure you could tell. Then, after that, we have the well-known second law, which is that the net force is equal to its mass, so this is mass in kilograms, times the acceleration in meters per second squared. So this is kilograms, and this is meters per second squared, okay? Then the third law is the law of action and reaction. So let's talk about the law of inertia. Well, as you could tell, inertia, these are pretty similar. They both have inertia in it. So let's talk about what inertia is. So imagine you have a block. Okay? If it's at rest or moving at a constant speed, that's the law of inertia. In forces, it's just if it has equal forces acting upon it. And in this case, it's just if it's at rest or moving at a constant speed. By constant speed, I do mean a constant velocity. Velocity is constant, so just know that. Okay, so let's talk a bit more about this. Okay, so what the inertial frame is a frame of reference in which an object, for example, let's say a car, has a constant velocity. That means that the acceleration equals to 0 meters per second squared. So no acceleration, and it has to be moving in a straight line. So that is what we mean when we refer to inertial frames of reference. Now let's go into relativity a bit. So let's talk about special relativity. Newtonian relativity states that physical laws should be the same no matter what the inertial frame of reference is. But, they can vary across non-inertial ones, but we're not dealing with that because we're mainly covering special relativity, not general relativity. And special relativity only applies for cases that Newtonian laws don't apply for. Now, imagine you're in space. Perfect that this is black. Let's say a couple stars right here. Not the best at drawing. But yeah, you got a couple stars and you're in a ship, okay? This is you. You're in a ship. Now, if you're if there's nothing around you, let's say there's nothing, it's empty space, okay? Empty space. This is empty. You can't measure your speed relative to empty space. There's nothing there to compare it to. Same with distance. You can't measure distance, velocity, you can't measure anything. But let's say there is another ship. Let's say it's your friend, okay? Now, you can measure your speed and velocity relative to him. Same with the distance. So there basically has to be another thing that you compare to, or you're relative to. So, let's say you're in the spaceship, okay? This is inside the spaceship, and you're moving at a constant speed. Let's say the velocity is equal to 0.25 c, so a quarter of the speed of light. If you were to flip a coin, it would obey the same law of physics as if you were on Earth. Of course, gravity is less in space, but the same laws of physics still apply. Okay? And what this does, this encompasses the first postulate of special relativity, which is states that all laws of physics are valid no matter what the perspective of the observer is, as long as they're moving at a uniform velocity. Now, let's say you're moving on a ship, okay? That's not the best ship drawing. I'm gonna try to improve this. You're on a ship, okay? And you're moving at, let's say, half the speed of light. And there's a tower. And let's say it's shining light at you. No matter your speed, distance, whatever, the speed of light relative to you will always stay the same. It's always going to be the same. And that's the second postulate of special relativity. That's the speed of light is constant, which is why we use the letter c, which equals to 3 times 10 to the 8 meters per second. So please remember this. Whenever we're dealing with formulas and stuff like that, we do it in meters per second. So remember this. This is pretty important. Okay? Mostly you'll be given it, but just in case, alright? And this is, of course, in a vacuum. It's constant. Now let's go a bit into general relativity. So if you remember earlier, I did talk about how and when general relativity came about. So it deals with cases that deal with space and time. It's basically a theory about gravity and how gravity is able to bend space-time, which is a very cool concept. Sadly, within the allotted amount of time, I cannot go over it with you, but I do recommend going further into it. So basically, the greater the mass of the object, the greater the gravitational force. So think about this. Let's say we have a blanket, okay? And we have a steel ball. And we'll drop it on the blanket. What will happen? Yep, that's right. It'll curve. It'll curve and that ball will sit right at the bottom. Okay? And what happens if I roll a little marble that's a lot tinier around? It'll go sort of in circles, kind of orbiting around it. And this explains how this is kind of a basic concept. Of course, it is more complicated than this, but it's a basic concept to help you understand this. And it also does affect time. So, so let's go into one of my favorite things about special relativity. Honestly, my favorite. And I loved for you to research further about this because this is very interesting to me. So let's say you're on a train. I cannot draw the best, so please forgive my drawing. And it's going at, let's say, half the speed of light. That looks like a 6. Half the speed of light, okay? If you're in the train and you have a mirror, let's make this a bit bigger. So you have a mirror, and let's say this is you. In order for the light to reach you, how would it travel? Sorry. How would it travel? Well, it'd just have to travel this distance between you two. So it's not that much of a distance, right? Now, imagine someone's outside the train and they look in, okay? It's not going to be the same because the train is going to travel, right? Because it's going to change time because the velocity is constant. Now, what the light will do is basically have to do kind of a triangular like thing. So, since the velocities are equal, remember what we said earlier, that velocity equals to 0.5 speed of light, half the speed of light. And we know velocity equals to displacement, over time. Now, if you remember earlier, the person on the train, they only had that one little short distance, but the person off the train had a bit longer of a distance. Okay? We know that speed of light is constant, equals d over t. And we know that this d is greater for the observer. So that means t equals d over 0.5c. So since the d is greater, that means time is greater. So I know this is a very complicated subject. That means that the time passed by the observer is actually greater than the time passed by the person on the moving object. I, I, I just think that's crazy and amazing. Now, this phenomenon is called time dilation, which is defined as how the perspective time changes based on motion. For example, I'll give you another analogy right now. You have two twins. They're on Earth. Okay, let's say this twin. He goes on a spaceship and starts traveling at a very fast speed, let's say. When he returns, let's say they're both 20, okay? When the first person returns, he'll be maybe slightly older, maybe 20.6. But the other person is like 60. Of course, in time dilation, this is a very specific case, and we're just doing a general analogy here. So, it's basically the time slowed down for the person going faster versus the one who stayed on Earth, his life passed by. And that goes a bit over time dilation. Now, there are two types of times that, okay, when I say that, I know it sounds weird. So there's proper time. So what proper time is imagine you're in the spaceship. You in the spaceship, relative to the spaceship, you aren't moving. You stay stationary. Relative to the spaceship. So what it is, it's how time passes relative to the same position in space. Now, if I'm outside, I'm sorry, if I'm outside the spaceship and I'm measuring the time for this, it's going to be different because for me, it's going to a different position in space. Now, this is called relativistic time. And it's basically how the observer views time. Now, if you remember from earlier, the observer's time is always going to be greater than the person who's moving with the object. So therefore, relativistic time is always greater than proper time. All right? I'm going to give you a quick question to do. So, let's say I'm traveling at zero point 0.5 speed of light, okay? And I want to tell how many seconds would pass for a person on Earth if 3,600 seconds passes for the person on the thing. Now, what formula do we have to use? Well, we have to use gamma. Now, what is gamma? I'm sure you're wondering. Gamma is the ratio between measurements that observers will make in different frames that are moving relative to each other. So gamma is equal to the square root of 1 minus v squared over c squared. This is gamma. And this is used in the time dilation formula. In this case, it's t equals to t0 over 1 minus v squared over c squared. And I'm sure you can tell that that means that v squared has to be less or equal to c squared, or just v less than equal to c. Which is actually kind of an interesting phenomenon because we have witnessed speeds that are faster than the speed of light. For example, the universe is actually expanding at a faster rate compared to light. But of course, this is a flaw, but there are many flaws in physics, and our goal is to find these flaws, fix them, and improve our understanding of the universe itself. So, let's go more into this equation. So I have t equal to 3,600 seconds over square root of 1 minus 0.5 c squared over c squared. I'm sure you're able to do this. Just plug this into your calculators, and you should get the relativistic time. This is relativistic time. Okay? So yes, I'll remind you again. T equals to t0 over, this is proper time by the way, 1 minus v squared over c squared. And of course, this is root. And this is gamma to the negative 1. Okay? Now that we talked about time dilation a bit, let's go into length contraction. So, when an object is moving at a high speed relative to an observer, a phenomenon called length contraction occurs. Imagine a ship. Okay? Its proper length is 1 meter. If it's moving at 99.5% c, so 99.5% the speed of light, and if you were to measure the ship from this side over here, what would you expect it to be? What would it be? 1 meter? 2 meters? Well, actually, it'd be 10 centimeters. 10 centimeters. And that's crazy. And this is what length contraction is. And of course, you only can measure it based on the direction of motion. So if you're standing like in front of it and it's coming towards you, you can't really see the length contraction because you're not looking at the direction of motion. And there are two types of lengths. And when I say that, similar to time dilation, it's just like different ways of saying it. So there's proper length, which is the distance from 2 points that are relative to an observer. So you're in the ship and you measure the ship, it's 1 meter. Okay. Then there is relativistic length, which is the distance between 2 points that are moving relative to an observer. So we are outside the ship now and we're measuring it. And this is 10 centimeters. And it basically, what it's doing, it's starting to look thinner. It looks like it's contracting in on itself, thus why it's called length contraction. And from this, we can determine that proper length, so proper length, is going to be greater than relativistic length. Just to clarify, this is relativistic length. All right. And let me just show you the formula. Formula for length contraction. And I'll give you a question right now. So, the formula for length contraction is equal to, oh, sorry, it's equal to L0, sorry, yep, L to the square root of 1 minus V squared over C squared. This is your length. So this is observer, so relativistic, and this is proper. Okay. And of course, c is speed of light, velocity speed of the object, and 1 is 1. So this is a formula we use. So I'll give you a question right now. So I'm moving at 0.25 c. My proper length is 1 meter. Actually, let's make this more interesting. Let's make it more interesting. Why not? 0.5 c, and my length is 1.7 meters. My proper length. What is my relativistic length? So I'll let you calculate that right now. Alright, so the formula you should have set up is L is equal to 1.7 multiplied by the square root of 1 minus 0.5 c squared over c squared. This should be the formula you got, and you should have gotten an answer, which should be, let's see right now, let me calculate it right now. So we have 1.7 multiplied by the square root of 1 minus 0.25. You should get approximately 1.472 meters. So it shrinks. That's very cool in my opinion. So I have attached a worksheet and a Kahoot for you guys to do below, so please refer to that and have a good day.